Hello, everyone. In this lecture, we're going to talk about nonlinear machine learning models. There are a few common approaches to do nonlinear machine learning. One is manually designing nonlinear features. For example, you can include quadratic features explicitly, then it's nonlinear in the original space, okay? Nonlinear features. And the other is nonlinear kernels, where, if your machine learning model only depends on the inner product of your data, then originally you say my inner product, is, for example, 2 data points is just xm transpose xn, then it's linear. It's the L2 norm induced inner product. It gives you a linear cascade. But what if I design the inner product more complicated, okay? It's not in this way, but it's still a kind of inner product. It turns out that it can be thought of as sort of linear inner product in probably a high dimensional space, and it becomes nonlinear in the original space. So this is known as some kernel of xn and xm, nonlinear kernel. The third approach is composite nonlinear functions, composite learnable functions, where the idea is, what if I still have a linear cascade, something like this, okay? Then I will apply some nonlinear functions, for example, f, okay? For example, the f could be the sigma function. Then I would apply the linear transformation again, but with some different weights. Then, some other nonlinear functions, so on and so forth, Then eventually, since it's nonlinear, the whole system is nonlinear, but the entire model is differentiable so that you can still compute the partial derivative with respect to each of these weights, and you can learn the model, learn all these transformations in an end-to-end way, okay? So this is known as the neural network. And if you have many composite layers, then it's called deep learning, right? Okay, but this is just the simplest version of deep learning. And now, you can design different architectures for deep learning, which is beyond the scope of this course. But in this lecture, we're going to focus on the a very standard neural network, or the simplest setting of the neural network. We're going to show that first, nonlinear problem exists. And then we're going to show that with such model, stack of, you can think of each model as the logistic regression. Then the stack of logistic regression can solve the problem. And finally, we're going to show that we're going to develop a systematic way of how can I compute the derivative, okay, of the loss with respect to each of the weights. How can I develop a systematic framework, okay, for designing such neural network or computing its partial derivative. Okay. So first, I'm going to show that nonlinear problem exists, and this is obvious. So let's consider x is x1, x2. There are two features, and this is 0, 1, okay, 0, 1. After 4 points, 4 data points, this is 0. This is also 0. This is 1, okay? This is also 1. So the target is 0, 0, 1, 1, okay? And I name these samples like this is my first data point, this is my second data point, this is my third data point, and this is my fourth data point, okay? So of course I can use different colors to show these samples. Okay. So obviously this problem cannot be perfectly solved by linear regression, because when you do linear regression, the decision boundary is a linear line or a fine line in the x1, x2 space, right? Because in linear regression, you have the W transpose X plus B, the sigmoid function of that. You would like to, you know, the decision boundary is this equals 0.5. Then it's equivalent to say Wx transpose plus B is 0, then it's kind of a linear line. You can choose different W or different B's, okay? But now if you choose a line, if you cut a line like this and you say, this is my positive samples, okay? Your predicted positive samples, then you make an error for this point, right? Because your decision boundary says, oh, this half space should be predicted as positive, but this point is 0. Similarly, if you have a decision boundary here, then, you know, 2 of them is incorrect. This is incorrect, and this is also incorrect. So it's obvious that you cannot solve this problem by a linear classifier. So this shows that nonlinear problem exists. I'm going to show that if I stack multiple logistic regression units, I can solve this problem. And by the end of the logistic regression unit, it's actually linear, right? So let's consider this. Let's transform x1, x2 into the H space, okay? Into an H1, H2 space. And my H1 is a logistic regression unit, okay, based on x1, x2. So based on x1, x2, I design a logistic regression unit such that it's predicting whether my data points is in this half space. This is my H1, okay? If a point's in this half space, then H1 would predict something greater than 0.5. And if some points is on this half space, it will predict something less than 0.5, okay? And then I can adjust the weight of my H1 logistic regression unit and make my, make the slope here very sharp, okay? Because this is the distance, but you should compute the distance. Then I can adjust the weight of W and make my prediction very sharp, right? Then I can say the points in this half space is near 1. It's almost 1. Maybe it's 0.8, 0.9, or 0.99. But the point here is almost 0. Maybe it's 0.01, something like that. Okay, so this is my first logistic regression unit. And this is my second logistic regression unit. So I design another logistic regression unit saying if the points are here, then it gives me 0. So it gives me 1. And if the point is here, it gives me 0. Okay. Then where's my first data point? The first data point is here, right? It's not in the lower half space of H1, but it's indeed in the lower half space of H2. Okay. So the first data point, it should be H1 for the first data point should be 0. And H2 for the first data point should be 1. Okay, so it's 0, 1. The first data point, H1 is this point. And similarly, for this data point, the fourth data point, it should be similar, okay? This is the same, it should be H4. And for the third data point, it's in the lower half space of the both decision boundaries, and it should be 1, 1. Okay, so this is H3. And for the second data point, it's in the upper half space of both decision boundaries, so it should be 0, 0. H2. Okay. And I know that H1, H4 corresponds to the positive samples. And the third data point and the second data point, they are negative samples. Okay, they're negative samples. Okay, so this time I can do another linear classification built upon H1, H2 instead of X1, X2. Okay, and I do a classification, I do a prediction. So I have a third classifier, the digital regression unit, predicting all the points in this direction as 1, and all the points in this direction as 0. Then you make a perfect prediction on these 4 samples, right? So this shows that the stack of logistic regression can solve the nonlinear problem. At least it can solve this problem, okay? So what I suggest is H1 is the sigmoid function of W1 transpose X plus B1. H2 is sigmoid function of W2 transpose X plus B2. And my final prediction Y is sigmoid W3 transpose X plus B3, okay? Then how can I learn this model? Can I just compute the gradient and do gradient-based update? Yes, of course, because this model is differentiable, right? Every function here is differentiable, so the entire model is differentiable. So you can represent Y as the, 1 plus exponential of minus W3X minus plus B3. Okay. Oh, so this is not X, okay? This is H, where H is H1, H2. Okay. Then I would say this is 1 plus exponential of minus, okay? So this is the W transpose H. So I can say W3 for the first element for H1 plus W3 for the second element for H2 plus B3. Then you can put X, H1, H2 inside this. Okay, then the function is differentiable, then definitely you can compute the partial derivative with all these weights, right? Then you can do the gradient update. But obviously, this is not a serious attempt to compute a partial derivative because it's overcomplicated and we cannot easily do it by either paper-based derivation or by implementation. It's overcomplicated. So that's why we need to have a systematic framework in defining the neural network in a clear manner, and then everything is manageable. The computation is manageable and human understandable, okay? So we need a systematic, design of such stack of digital regression units, okay? And here is what we do. So let's consider a unit. A unit is also known as the neuron. It's analogous to the neuron in our brain. It's somehow a simplified version or a simplified model of our neuron really looks like this. It has some input, right? And it has some output. And the input takes signal from some other, the input is the signal of some other neuron's output, okay? And then the neuron says, okay, I take the weighted sum of this input signal. Okay. Then I have maybe a thresholding function, and if it's greater than a threshold, maybe I call it tau, but you can put tau into B, so I can say it's greater than 0, then my output is 1, okay? 1 is 1, or 0 otherwise, okay? So this is the oversimplified version of how the neuron in human brains work. But we can somehow relax the hard thresholding function as some other functions. So I will suggest a neuron, a more generalized neuron or a unit is some function of W1, X1 plus this, but I can write compactly as W transpose X plus B, okay? Where F is a nonlinear function, okay? For example, it can be the sigmoid function. It basically takes the output of other neurons as input, and it processes the information in a simple way, which is a linear transformation. Then it becomes a scalar. Then you compute a nonlinear function, and it becomes your output. This is also known as the activation function. Okay. And this model is also known as a neuron or a unit or sometimes known as node or some other terminologies, okay? So, I mean, we have done nothing. This is just a logistic regression unit, okay? So now the next thing is we'd like to stack these things together and make a multi-layer neural network, okay? So I would suggest we stack the things together, okay? So we have a few layers. And the bottom layer is the input, okay? It's basically the features, for example, X1, X2, X3. And these are the middle layers, okay? And this is the output layer. The output layer really depends on your task. For example, if you have a linear regression, then it's just a single unit. And the activation for the output layer is the identity function. You have no activation. Basically, you are doing a linear regression on this feature, right? So if you are doing the classification, if it's a binary classification, you can do logistic regression. If it's a multi-way classification, you can do softmax regression. Then it's basically a linear model on these features, okay? So this is the output layer, depends on the task. This is the input features, okay, data features. Okay. These are known as the hidden layers. The connections are like this. So every node is connected to all the nodes in the lower layer, but no other nodes. So it's connected in this way. Okay. Okay. These are known as the hidden layers. Okay. And by the way, when we count the number of layers of a neural network, usually the input layer doesn't count. So this is a 3-layer neural network because you have 3 layers of parameters, okay? The input layer is just the features, it doesn't count. So the hidden layers are layer-wise fully connected. Okay, which means the output of a lower layer is the input of every node in the upper layer, and vice versa. You know, the input of a node in the upper layer is all the nodes in the lower layer, right? But there's no connections of nodes within a layer, okay? And there's no skipping connections. For example, I have a connection like this. We don't have that connections. So this is the classic neural network. Of course, it's not the perfect model. You can violate the fully connected constraints. For example, you can have the skip connections. That's known to work very well. Or even you have the input skip connected to every layer. I mean, that works even better. But for the purpose of this course, we focus on the classic model, which is this, okay? And this is known as the fully connected neural network or feed-forward neural network. Okay, by feed-forward just means, you know, every lower layer is feeding to every upper layer. Okay. And I'm just going to give one more terminology. This is also known as a perceptron. So this is also known as the multi-layer fully connected perceptron. Okay, it's basically the same thing. Okay. So with the knowledge that we have learned so far, we almost identify what are the key issues for the neural network, right? We know that you know, you can define the loss on the output layer as if you are doing a linear model because it's indeed linear in lower layers, right? It's the likelihood of your data, and the likelihood doesn't care much about how you parameterize the distribution, right? So you can apply the same loss, like the cross-entropy loss, mean square error loss on the output layer, as if you are doing linear model on the last layer. So the main issue is how can I compute the output, right? How can I compute? So suppose all the weights are known, or how can I compute the prediction? The second question is how can I train it? Train the model. Okay. And we know that, you know, first, this model is non-convex, and this is easy to show. If I want to show a model is not convex, I only need to give one example of 2 points and a weight, the lambda weight that violates the, you know, the convex constraint. That is easy to show. You can use the symmetric of your weights. So for example, you pull this node to here and you pull this node to here, you get the same model. You swap 2 sets of W's, you make use of the symmetry of your weights, and they are all good, okay? They are all good, so they're symmetric, okay? So I call it W1, W2, it's the same as W2, W1, they're all good. But if you tie them together and you say W1 is just W2, then it's no good. So you show, you know, in this example, you can show this is H1, H2. You can say H2, H1, okay? Then I interpolate these 2 things and I say H1, H2 must be the same. Then I only have one classifier, so I have this, you know, H1 must be the same as H2. You know, it's not good. Then it shows that, you know, the curve, at least for some, you know, slice of the error surface is non-convex, then it's non-convex, okay? So it's non-convex. But non-convex optimization can also be optimized by gradient-based approach. But in this case, it may not go to the global optimum. Sometimes, if you start from here, you may start at some local optimum. Okay, so it can also be optimized by gradient-based approach. Okay. But how can I compute the gradient? So these are my two questions. First question, how can I compute the output? Second question, how can I compute the gradient? Okay. So I would suggest a recursive algorithm, how can I compute the output? It's by definition, I compute the output of every layer. Then, if I'm done with all the layers, then the entire neural network is done. Okay. When I compute the gradient, then, the chain rule starts from the end. Okay. I first compute the partial derivative of this. And then if this partial derivative is known, I compute the partial derivative of this. Okay. It goes in the recursive way or an iterative way, then I can solve the gradient for entire model, right? So let's do this. So I'm going to compute the output of the model, and this is given by an algorithm called forward propagation. Okay, which is FP. So basically, the idea is you compute the output layer by layer. Okay, the lowest layer is just the feature. Then you compute the output of this. Then you compute the output of that based on how you define the semantics of these neurons. Okay, the computation will be a recursive algorithm. The output or the value of each layer, and I call it YL. Okay, for the lowest layer, it's Y0. So X is actually Y0. It's just 1. Then this is Y1. This is Y2. It's so on and so forth. And the final layer is YL. Okay. So when we talk about a recursive algorithm, we always have 3 steps. One is the initialization, and the other is the recursion formula, and the third is the termination. So the initialization, how can I get started? Okay. And then recursion step. If you know the previous result, what is the next thing? And when do you finish your algorithm? So this is different from mathematical induction. Mathematical induction, you can do infinite induction or transfinite induction. But in algorithms, everything must terminate somehow in finite steps. Okay, so it must terminate. So the initialization is Y0 is X. It's just the definition of the input layer. Good. The recursive algorithm, the recursive step says, suppose I know YL minus 1. The question is to compute, the goal is to compute YL. And this is not difficult. So I can say YL for point, let's zoom in and I consider a pair of consecutive layers, one of these things, okay? It's basically a linear transformation and then a nonlinear activation function. So why not, let's say my linear transformation is, I call it, define a Z for the nth layer, okay? C for the nth layer, I for node I is Wij xj. But you take the summation over different j's, okay, plus bi. The b is the bias for the ith node, okay? So this is the pre-activation value. Then after you apply the activation function, which is the FCIL, okay? So this is just the definition of the unit here, right? So one unit is defined in this way. So I'm just writing out in this way. Then in the vector form, so this is the pointwise form, but in the vector form, I can concisely write in Z as a vector, okay, is a W X plus B, where X, this is not X, this is the Y L minus 1. This is the Y L minus 1, okay, plus B. And Y for the nth layer, the Z is the nth layer, is the activation function on Z. Okay, here the activation function F is a pointwise, usually it's a pointwise activation function, but in some cases like softmax it's not pointwise. So pointwise activation function just means if you have a sigmoid over a vector, I call it C1, C2, C3, it's the same as saying I apply sigmoid function to every element of that vector, okay? So something like this. So it's the, then let's do a quick exercise on the dimensions, okay? So here, the X, so I assume that there are nx units in the lower layer and ny units in the upper layer. How about I call it n lower layer and n upper layer? Okay. Then, the input is the y L minus 1 has NL units, okay? And the output YL is the number of upper units, okay? But I can also say, oh, I don't think I need the L minus 1 or L. So I can say NL minus 1 and NL. So the notation is really ugly. Why not? Let's say NL minus 1. So N just means the number of units. Okay, now it looks better. Okay. And similarly, Z has the same shape as Y, right? Okay. And B, of course, has the same shape as Y and Z, okay? And W is actually a matrix, and it's the upper layer times the lower layer. So it's the NL times the NL minus 1, okay? So if you multiply NL times NL minus 1 with a vector of NL minus 1, it gives you a vector of NL, then it gives you Y, right? So this is the recursion. And termination when L equals L. It's trivial, but in an algorithm, you must make sure your algorithm terminates at some point. Okay, so the forward propagation is done. So in this way, you can compute the values for each layer one by one, starting from the lowest layer. And when you compute the value for the output layer, then you are done. And the second question is, how can I compute the derivative? How can I compute the derivative? So the derivative is computed by chain rule, and chain rule is you always compute the partial derivative of the outer function, and then you gradually append the derivative of each function, of the composite function, each layer of the composite function, and you also do it in a recursive way, right? This is how I did in manual computation of the derivatives. So now you can do the same thing. In the forward path, you compute the output. You start from the lowest layer, then you compute the derivative to the output layer. Then you can compute the partial derivative of the output layer, then you go back, okay? Layer by layer, then you compute the partial derivative of all layers. So it's also a recursive algorithm. Starting from the upper layer, then you compute the partial derivative of the lower layer. So it's known as the back propagation. Or BP. Okay. Now the next question is, what is the recursive variable for this algorithm? So can I do the partial derivative of J with respect to W for a layer? Oh, by the way, so the layer here, the W here is also for a particular layer, okay, L and W, but sometimes you have too many notations, and it's a little bit confusing whether my W here should be called as WL or WL minus one. So we typically call it as WL, but if you consider a recursive step, you can omit the layer if it's self-clear, right? But in here, the question is, shall we do the partial derivative of the loss with respect to the W of different layers? It turns out that it's not a good idea because you compute Y from L from the lower layer, but you inner product it with the weight L, then you compute the Y, here. Okay, so there's no direct connection between WL and WL minus one, right? So when you do the recursion on WL, you stopped here, right? You cannot do further back propagation. You need to backtrack a little bit and you come back to this variable, then you go back, okay? So this seems to be some complication, and you should not go with the W as your recursion variable. Rather, you should use the partial derivative of Y or the partial derivative of Z. They don't differ too much. You do the recursion variable on that, and then as a side product, you compute the partial derivative with respect to W for each layer, okay? So this is not a good idea. It should be a recursion on partial derivative of J with respect to either YL or partial derivative J with respect to CL, okay? So I will choose this one. I think it's different from my lecture notes, but it doesn't matter. So when we talk about recursion, we always have the initialization recursive step and termination. the initialization is the partial derivative. I'm doing this, okay? Partial derivative of J with respect to Z last layer. This depends on the task, and this depends on your loss and what kind of probability assumption you have, okay? Suppose you are doing the generalized linear model, then this is Y minus T. Okay, we have seen it for many times. Okay, done. So this depends on the task and probabilistic assumptions, okay? And this is the formula for generalized linear model, including softmax or logistic regression and linear regression. And of course, the F function for the last layer should be the canonical response function, okay? Otherwise, you don't get this property. The recursion step should be suppose partial derivative of J with respect to ZL is known. What is the partial derivative of J with respect to ZL minus 1? Okay, so this is my recursion question. So I would compute the partial derivative of J with respect to Z, okay? I can say the partial derivative of J, I want to copy this again. And I don't have to have that many nodes. I only need a few nodes to illustrate the process. So I don't even have to copy, I can redraw a diagram. Okay. So the assumption is the partial derivative with respect to these nodes are known, and how can I compute the partial derivative of these nodes, okay? So what I suggest is partial derivative of y L minus 1 for a particular I is, it depends on how you compute it, right? And you compute it in this way. So the partial derivative of one I, J with respect to this, is the partial derivative of J with respect to Cj L minus 1 times the partial derivative of Cj L minus 1 divided by partial derivative of y L minus 1, okay? Because it's the chain rule, you can cancel them out, and this is known, and this is the Wji. Okay, or Wij. It depends on whether your upper layer is I or the lower layer is I. So let's consider a matrix W. So this is the W matrix. So if my lower layer is a thin layer, then you get a point, which is this point. So it should be the upper index first, then the lower index. So it should be the upper index Wij. Okay, is that correct? So this is incorrect. Because I mentioned if you cancel things out, it's the wrong understanding of the derivative. The derivative is a notation, it's not a fraction. You divide a number by another number. No, it's wrong. The reason why it's wrong is because your J, this is your J, okay? It's a function of Y of this node, that node, and the third node, okay? J is a function of this node, and this node. And for a particular node to think of, which is the jth node, this node affects j not only through this path, but also through this path, and also through this path. So the effect of how j affects how this node affects your loss is the summation over how it affects the output in each path. So you should sum over j. Okay. If you don't have the summation, it's even invalid. The equation doesn't even make sense. What is j? You haven't even defined j. Okay. It's not for arbitrary j, because when you compute arbitrary j, the results are different. But here you don't even have a j here. Okay. So this is invalid. Okay. The mathematical equation itself is meaningless because you don't know what is j. Okay. And even if you say it's arbitrary j, or for some j, it's wrong because this node affects the loss in different paths, and the partial derivatives should be summed together to make it the total derivative. Okay. So this is the summation here. This is very important. So this is the first step. But if you have the summation, then this is good. Okay. So this term is known, and this term is also known because it's just the wij. Okay. Then this term is known. Then I can compute the partial derivative of j with respect to ci L minus 1 as the partial derivative of j with respect to okay. This time it's correct because the y and z, the f function is a scalar function. It's a pointwise function, so that ci only affects yi in a single path by the pointwise f function. Okay, so this time is correct. And what is this? Oh, this is known. So this term is known. And what is this? This term is the f prime. Okay, because we know y is f of z. Okay, for some superscript, subscript. Then if you consider the partial derivative of y with respect to z, it's just the derivative of f at that point. Okay, so this is f prime. And for the sigmoid function, it's just the sigma 1 over sigma. For different functions, you just compute the partial derivative of the activation function by itself. But if it's a softmax function, then you cannot have this, okay? Because in the softmax function, the z affects y in different paths. So for the sigmoid function, it's just this, okay? But for other functions, you just compute the partial derivative of that function itself. Okay. So we're done. Termination is when L equals 0. You don't have to compute L equals 0 because the partial derivative of the input in most cases doesn't make sense. But in some cases, it may make sense, which is the adversarial example. But when we train the model, we cannot modify my data points. So we can say when L equals 1. Done. Okay, but our question is to compute the partial derivative of J with respect to W and partial derivative of J with respect to B. Okay, so we can very easily compute that from these two equations. Okay. So what is the partial derivative of J with respect to W? Ij. So what is the partial derivative of J with respect to B, okay, it's the same as partial derivative of J with respect to Z, okay? So the partial derivative of J with respect to B for that layer is the partial derivative of J with respect to B. Sorry, Z for that layer, okay? So this is the Z. Based on Z, you compute Y, where Z is the inner product of the lower layer, Y minus 1, and the W, L, and BL, okay? And with respect to W, I mean, here I'm mainly using the pointwise notation. I have the Wij is actually multiplied by, Yi, okay, the lower input. So it's the partial derivative of J with respect to Z upper layer I, okay, for the lower L times the lower layers output, which is Y, minus 1 for the Jth element, okay? So I know the superscript and subscript are very confusing, but I guess you at least need to do it once a lifetime. And you need to derive the details once in your lifetime. So that's why we have the homework to do the matrix form. So I don't want to do it. I mean, I have the cheat sheet. I did it. Then, during implementation, you can prepare the cheat sheet and you can implement it layer by layer, okay? But, usually we do the implementation by auto-diff tools. So implementing backpropagation is no longer popular these days. It's almost obsolete. But when I was a PhD student, I implemented the C++ auto-diff tool, which is still available on GitHub. I mean, it's not a fancy tool. I cannot use GPU. I don't know how to do GPU programming, but I think it's still good for pedagogical purposes. And I guess once a lifetime, you still want to implement a deep neural network by yourself, okay? But in implementation, we have very good tool that directly gives you the derivative. As long as you can define how they are computed. Okay, good. So we basically solved the two major questions. How can I compute the output of a neural network? The output of the neural network is computed from the lower layer to the upper layer. This is known as the forward propagation. It's basically the definition of how you construct the neural network, or what does it mean by a neuron. Then you just put the definition here, then you get the forward pass. And the backward pass is known as the backward propagation algorithm, or the BP algorithm, which is computing the partial derivative of your loss with respect to your weights. Actually, the recursive variable is on the output or the pre-activation value, okay? You do it from the highest layer to the lower layer, then you get the partial derivative of J with respect to Z. Then you can compute the partial derivative of J with respect to W and B very easily. Okay? This is known and this is also known. Okay, so every term is known. So all the things can be computed very easily. And your homework is to do the matrix form. And I have the cheat sheet, okay, but I guess you still want to do it yourself. Okay, I have a few other questions. What if fully connected neural network? Or what if I have multiple connections? I have skip connections or duplicate connections. So let's say this is my set of neurons like this, okay? How can I do that? Okay. So you know the gradient, computing the gradient is a linear process. So the partial derivative of J, you know, with respect to this layer. Okay, so let's call it X. I mean, it doesn't necessarily to be the input features. Maybe it's on some lower layer. But the partial derivative of J with respect to this X, you know, is actually the partial derivative of J with respect to all paths, okay? So you can think of it path 1 of partial derivative of path 1 with respect to X, okay? But you have different paths, so you can take the summation of them, right? So it's exactly the same thing here. So it essentially says you can do the backpropagation here, okay? And you can do the backpropagation here and backpropagation here. And what you need to do is you take the summation, you sum over all the partial derivatives, it gives you the derivative for this layer, okay? So this is one thing. What if not fully connected? You have multiple connections or multiple dependency paths, you just sum them together, okay? Another thing is tied weights, okay? So in some cases, you know, your neural network has the same weights for different layers. Okay, for example, this is to process time series data, but you don't know how many steps you have. So these weights are all the same. Right? How can we do that? So in this case, you first treat them differently and you sum them together. Okay, so this is saying, why not let's assume my loss is a function of W1, W2, W3, W4, okay? And then I say W1 is actually W, W2 is actually also W, so on and so forth. Then the partial derivative of J with respect to my W is the summation over partial derivative of J with respect to each of the W, okay, for different i's. Then the partial derivative of Wi with respect to W, but this is one, okay, or at least it's an identity matrix. You know, again, you are considering the total derivative, okay? So you just have the summation here. So this is the tied weights. And the third thing is, what if you
losses, okay? So maybe I'm doing classification here, I'm doing regression there, I'm doing something here, then how can I do backpropagation?
So if your loss is J1 and plus J2, for example, then the partial derivative of J with respect to W is actually the partial derivative of J1 with respect to W plus the partial derivative of J2 with respect to W, right? So again, it's the sum, okay? You can do the backpropagation for each thing, but we don't do that separately. You can group them together and do the backpropagation. Because, you know, if you have the J here and J there, you know, then the partial derivative for X4 is actually, so let's say the partial derivative with respect to X, So let's call this layer, let's call them Y's, okay? To be consistent with our notations. Y4 is actually the partial derivative of J1 with respect to Y4 plus the partial derivative of J2 with respect to Y4, right? Then, you know, the partial derivative of J with respect to Y3 is actually the partial derivative of J with respect to Y3 times the partial derivative of J of Y3 with respect to, of Y4 with respect to Y3, right? Then this is local known, and this can be computed separately. So this means if you have two losses, you only need to group them together based on the nearest common node, okay? And then you do backpropagation together once. So the computation for backpropagation is linear, right? So how much time you take for forward propagation is roughly the time you take for backpropagation. Okay, so all these will give us the autodiff algorithm. So the autodiff algorithm is, I know how the values, the variables are computed. Then I can compute the derivative automatically. We don't have to compute it manually, okay? So that's why nowadays, not many people implement the backpropagation by yourself. And you just apply some toolkit and it automatically gives you the derivative. So autodiff algorithm is, you first do a topological sort. Okay. It means that if a computation is, the computation of a variable depends on some other variable, then the other variable must be sorted before the dependent variable, okay? So now you have a bunch of variables or a bunch of layers, okay? They are topologically sorted, and you can have many layers, right? You can have many connections, or you can do things like this, okay, as you like. This is known as the computational graph. For valid computational graph, there's no loop, okay? So it doesn't make sense, the variable depends on that variable, and then that variable depends on this variable. Then it doesn't make sense. You have an infinite loop in computing the variable. It either gives you a fixed point, or it gives you some divergent result, or it becomes a dynamic system. So that is not the case. We consider a one step of computation, and there's no loop in the whole process, okay? Then the autodiff algorithm works like this. For L, a layer from the last layer to the first layer, okay, the 0th layer, or if you don't care about the input, then it's the 0th layer. You apply loss, if any, okay? Apply the local loss, the loss for this step, okay? So, if you have a loss here, if you have the loss there, then, if you are at this layer, you should compute the partial derivative of J with respect to Z in your case, okay? Then if you are in this layer, then you can compute the partial derivative of J with respect to that Z first, okay? Apply Z. It should be the partial derivative of J with respect to the Z for this layer, plus equals partial derivative of J with respect to J, apply loss Ji, for example, okay? Then for the child nodes of this layer, okay? So, if you are at this layer, the child node is this, is that, okay? So I say that for the child node, each of the child node is C, okay? Then the partial derivative of J with respect to C is the backpropagation, okay, from the current step. Okay, this is C, So you basically apply the recursive step we have computed in here, okay, and you add the partial derivative to do the backpropagation for all the child nodes of the current node, okay? And when it's done, you move to the lower layer. You backprop to here, you backprop to there, and you move to this layer. It has no child node, ignore that. And you go here, you apply the loss first. You first have the add the loss. So you already have some partial derivative from this layer, which is inherited from J1. but you plus the partial derivative of J2 with that layer, and then you backprop to here, and then you compute this layer, you backprop to here, then you go to this layer, you backprop to here, and you go to this layer, you backprop to there, okay? And compute the partial derivative of J with respect to W for each layer based on these equations, and tie weights if necessary. Okay, so this is a very brief introduction to neural networks. And definitely there are many more topics in deep learning or neural networks, ranging from theory to applications, and applications in different domains. For myself, I also teach the deep learning for NLP course. But in this lecture, or for the purpose of this course, we mainly focus on why a multi-layer neural network can solve nonlinear problems, and how can I train a nonlinear network by backpropagation. Okay, thanks for watching the video. See you next time.